So, hey everybody. Week 7, you made it. So today is the 13th of April. Next week is spring break. We have this week's assignment is going to be the last canned assignment that you're going to work on. There may be some optional ones that you can do conditionally, but the first week back from spring break, the thing that I want you to pitch, the week that we come back during the class, I'd like everybody to say a few words about some ideas that you have for a project. And it can be crazy, and you don't necessarily need to know how to do it, but the point is that you'll have, including the week after spring break, you'll have 6 weeks before the end of the semester, before classes end, to actually do a project. And I want to say a little bit more about that at the beginning of class. How did everybody do on this last week's assignment with Gazebo and the plugins and all that? I had a couple of things, a new one on me that I had never seen before. I worked with one of you on Friday evening after office hours for a while because the student's Zacro file wasn't represented the robot in Gazebo, but the robot went crazy and didn't balance properly in the simulation. And I was like, we'll just clean up your Zacro file. And the Zacro file actually looked pretty good to me, and when I looked at it more and more, it was a really nicely written Zacro file. Well, nice use of macros. Couldn't figure it out, so finally I took the Zacro file and put it on my computer, and it ran perfectly. Backtrack. I think there was what I believe happened is that the executable for the Edgeemit balancing plugin had gotten corrupted somehow during a bad build, and when we deleted the build and develop directories and also the install directory, which the student had. If you do a cat-can make install, it'll create an install directory. Don't do cat-can make install. That's not something we need to do in this course, just cat-can make. So we deleted all 3 of those directories, did a clean build, and everything worked perfectly. I've never actually seen that error before, where the executable was running, it was publishing topics, and yet it was sort of zombied. And unfortunately, these things are ephemeral, so it's hard to recreate that kind of thing. Yes?
The same error that happened with me too, but then the only thing that I had to change was the inertia position. It was too much, too down for the if I moved it up, it started something properly. And it was working well on the other laptop that I had.
So I didn't quite understand, what was the problem and how did you solve it?
So I was having a similar error where for my machine it was working fine. For the other machine, it was working fine, but on my machine the robot was just doing some weird stuff.
Yep, and so how did you solve it?
Then I just changed the mass value in my element of the body, the inertia position. And when I moved it up a little, it just started working properly.
Yeah, the center of mass for the Edgeemit needs to be in the middle of the body. And it's fairly forgiving. If you make it twice as high or half as high, it will still balance. So that's the beauty of feedback control. Any other surprises? So the reason that I gave you this assignment is that many ROS users don't make effective use of Gazebo, and that's trying to be a decent programmer without learning how to use the debugger. You won't ever become a decent programmer if you don't learn how to use the debugger. That's one of the adult skills that people who program a lot use. And Gazebo similarly is one of the, it's a sophisticated tool that can do quite a lot for you, but you've got to be a sophisticated user in order to be able to make it work. So, and my goal is for you to come out of this course as being a solid ROS user with a good base with which you can learn any of the more advanced topics. Okay, so week 7. Before I talk about this week's assignment, I want to talk about projects. And so if we scroll down here to the independent project, I have posted on the class Dropbox, which is listed here, For your viewing pleasure, this is the same place you got the BeagleBone image, project reports. And this will give you a sense of how the classes are going. This is the 2015 project reports, 2016 project reports. There's more. And 2017 project reports. So, and one of the reasons that I switched to teaching this course with the EduMIPS is that I wanted everybody to get lots of hardware time with the machine, and this seemed to be a good way to do that. So I'd like you to peruse these. I'll show you a few just to give you a flavor on my computer here. So project reports for last year, project reports. This is one that I showed you a video of earlier in the semester. You may recall there's a YouTube video. Students set up 3 cameras and they calibrated, did hand-eye calibration with the robot and 3 cameras. And they were able to take and toss a small plastic ball towards the UR5. The cameras would track it, project its intersection with a point that was 20 centimeters off the wooden table, and move the arm to intercept the path of the ball. It was a pretty impressive project. And the, let's see, marsupial landing. This is one that I showed you a video of earlier. This was with a AR parrot drone, which is a low-cost, not very great quadcopter. And in this project, three students did it. The drone hovered around in the sky. The robot positioned itself underneath the drone, found it, searched for it, and found it. They both had AR tags on them, and then it commanded the drone to land on the top of the robot. And they were pretty ambitious because they made this landing pad on the top of the robot really small. If I was doing this, I advised them, I said I'd make it this big, because that way it's much more likely to land. On the YouTube channel for last year, if I go to YouTube 530.707, sorry, 530.707, you'll see a bunch of YouTube project demos interspersed with other things. This is the ball catching demo. Showing hand-eye calibration. So calibrating the different cameras. And so they've identified the camera pose in relation to the robot pose. And this is pretty impressive. So you can see, I think it's Jinbai is just got the ball and is tossing it back and forth between his hands. And in RViz, you can see down here on the right, I'll turn the lights out, you can see that it's displaying the ball's position in real time. I think you can just see down here, it's a little bit hard to see that because the ball is being displayed in purple. That was a good one. The real challenge here with the UR5 is that it doesn't move that fast. And so I'd say that the UR5 was really marginal to do this. And one of the reasons that he's bouncing the ball off of the floor is so it's got a good arc, and he's got at least a second or so to do the perception and move the robot. We may do a field trip to the underwater vehicle lab. So we've got 6 UR5s. We've got 2 underwater robots, and there's some prior art here in that Laughlin and Shaheen have written a ROS interface to these underwater robots. And this is opening up the user interface. forward here. And this is the view. These robots are about the size of a lunchbox. They're made out of plastic. And this is the view out of the forward-looking and downward-looking camera on the robot. And as they drove the robot around the test tank, this is a water tank that has 195 cubic meters of water. They're using the camera images to do SIFT image feature location and to do visual odometry. And they estimate both the position of the target features in the tank and the position of the robot itself in real time. And so this is a combination of off-the-shelf packages and custom packages that they wrote. And you can see this is the trajectory of the robot. So we've got two of these guys, and this is the point cloud that's resulting. That one's not mine. This is Rachel and Ryan's project from a few years ago. This is in Hackerman Hall, and this is the car that they put together. It's got a laser scanner on top. It's got an i7 microprocessor running a small brick. It's got Wi-Fi, and they're doing, that's Ryan there on the left sitting in the chair, and they're doing autonomous navigation where the robot is making the map and navigating using its laser scanner. And you can't, the production values of this video are great because you can't actually see the RViz representation of the map it's generating. So we've got two of these cars, each with a really nice, a super nice, high-quality Hokuyu laser sensor that does like 40 scans a second and is full daylight capable, so you can run outside. It's a pretty expensive sensor. It's worth about $5 grand. So their steering control is a little bit wonky. That's what you're hearing with the bangs. So you can browse these things and look at some of the project reports. Some students last year took the EduMips and did swarm navigation with them. This is the EduSwarm project, and there's a YouTube video of that. Let's see, the Thomas Chess, Drone Slam, file report. So Cora Dimming, Tyler Payne, and Annie Mao did a project where they put some sensors on the EduMips, and they did multi-robot SLAM navigation. So they had multiple robots. And what we found was that a lot of the standard SLAM navigation packages that are designed to work with laser scanners to have a full scan with maybe 100 or 200 points per scan and several scans per second, they didn't perform that great if you had a really slow scanning robot. And so their idea was to put an ultrasonic and infrared ranging sensor on a little extension on top of the EduMip and interfaced it electrically to the EduMip. And they rotated the robot around in a 360-degree rotation while taking ranges to get a scan. And what we found was that the standard packages for doing SLAM navigation, they really want to have pretty rich scans, and getting sort of one scan every several minutes wasn't rich enough to do great navigation. And so it did work, but it was things worked pretty slow. And it was impressive because they had 3 robots scanning simultaneously and combining information in a common package. And you can see that here, where these are the data from 1 robot, 2 robot, 3 robot, and these are the data combined from all 3 robots. So it did work, but what we learned was that scanning by just rotating the robot around isn't the world's greatest solution. And you can see theirs is a fairly complicated system. So on the course website, I just want to whet your appetite here. Here, on the course website, I bring your attention to, I'd like you to review some of the equipment that we have. Of course, we've got EduMips. We have a bunch of Turbot 2s, and you'll work with a simulation of the Turbot 2s with 5 of them, each with an onboard laptop. We have some Parrot AR drones, and these are okay. I'd really like to find something that's a little bit higher quality. One of the big problems with these drones is that they're very limited in their camera range. They have a forward-looking camera and a downward-looking camera, and you really got to just choose one. You can't switch back and forth easily between them in real time. A friend of mine, Daniel Kremers, has some ROS packages that interface to the AR drone, and unfortunately he hasn't updated them recently, so if you want to work with these, then you probably have to take a laptop that we have in the lab and load it up with ROS Hydro, which means you're going to have to load 14.04 Ubuntu, because last time I checked, these packages hadn't been updated to 16.04. But we do have a place to fly them in the Hydro lab. We've got 2 OpenROV version 2.8 drones. This is a new one that hasn't actually been produced yet. The ones that we have look like this. So we've got 2 of these. And they actually run a BeagleBone inside of them. And what Shaheen and Laughlin did when they did this project, this is a crappy camera that they have. It's got what's called it's a crappy camera, and so they got rid of this camera and they put an extra BeagleBone in here in the housing and an extra camera. And the job of that extra BeagleBone was just to handle the images and push them up the Ethernet cable. We've got 2 model cars, and this is the bill of materials of things that went into building it. So a lot of stuff, but they're assembled, and we have Rachel Hegeman is around, and she's going to help us out advising it. Lots of sources for additional sensors and actuators that we can suggest. These are on scale model cars. These were the original model car that we built it out of, or I say the students built it out of. We've got one of this model and one of the other model that's linked here, and added to them various electronics interfacing, batteries, an i7 CPU, an Ethernet switch, all of this on board the machine, and we have some local experts on how to use these things. So those are some ideas. So I'd like you to, and we're not limited to these robots. If there's some other thing that we want to, that you want that we can buy, then probably we can do that. And so please do take a look through the YouTube videos, search for the course number, and these project reports. All right? And what I'd like you to do the week we come back, probably on Thursday, I'm thinking, is I'd like to go around the room and have everybody get up for a few minutes and talk about a project that they're interested in doing. And if you want to do that individually, that's fine. If you want to seek a partner in crime and attract other partners in crime, this is your opportunity to pitch a project and attract partners, or to listen to a project and be attracted to it. I've found that it works best if teams aren't too big, because if teams aren't too big, then sometimes the actual workload can be uneven. So I think that 3 is probably an ideal team size. 4 is okay. If it's bigger than 4, I want a pretty good reason for it, because I want to make sure that everybody's getting an opportunity to participate fully in the conceptualization as well as the engineering, the actual detailed engineering. So we'll have a sort of an elevator pitch session probably the Thursday after spring break. And you don't have to have a fully formed idea. It can be crazy. That's okay. And maybe if you have a crazy idea that you don't think can be done, somebody from the class will think of a way to make it not so crazy so that it can actually be done. Any questions on the project? And from here on out, for what's going to happen in class is, from here on out, I'm going to give some supplementary lectures in things that you're going to need and you're probably going to want to know. So I'll give a supplementary presentation on namespacing, which if you want to use more than one robot is something you've got to do. I'll give a supplementary lecture on some of the newer ROS build tools, Cat can make tools, give a discussion on how we synchronize time in a precise fashion between multiple machines. That's really important when you're logging data on multiple machines. So how to do super nerdy time synchronization. I'll probably do an additional presentation on things like AR tags and laser scanners. Those are all useful things. Do an additional one probably on GPSs. ROS has very nice support for GPS, and I'll show you how to use a GPS daemon, which will allow you to use a GPS both to synchronize time on your machine to GPS time and also to distribute GPS time and location within a network of computers. And so these are all skill sets that are not important if you don't actually build real-world systems. But if you're going to actually build real-world systems, then actually making the clock sync matters a whole lot. And actually being able to get that GPS information and pushing it around the network matters a whole lot. Questions? And so the assignment that you'll be working on the week you get back is to write a project proposal, and that's going to be due on Tuesday, the second week after you get back. And this is what the project proposal will consist of: title, author, date, description of the project, software of new stuff that doesn't exist that you know you need to write, and stuff that you think you can use that's available in open source packages. What hardware do you need, and is it hardware that's available to you or hardware that we can make available to you from the course? A few students have done projects where they're working on a project that's related to their research, and they used a robot that was available in their research lab. Describe the availability. We do have funds to buy stuff if you need things. Not $100,000, but if we need to drop a few $1,000s to support some projects, then we can do that. Safety plan, are there any risks? And the other thing, I have a personal aversion to first-person shooter projects. So I won't say you can't do them, but ick. And so I discourage first-person shooter projects just because I think they're ick. Cite any references if you get ideas from different places. Remember that it's not plagiarism if you cite your sources. Come up with a project timeline. At that point, there will be 5 weeks left in the semester to do the project. And then each week, I'll ask you to submit a brief project progress report on what you accomplished last week, roadblocks you hit, roadblocks that you overcame, and so on. I'll do a brief supplementary lecture on how to do serial I/O in ROS. And yeah, so that's where we're going to go from here. Any questions? Okay. And the final project poster session will be when the exam would have been scheduled for this course if we had an exam. And I'll post a template for a project poster, and we have poster printers both in mechanical engineering and LCSR. I'll create a YouTube channel for this course, and if you upload videos to my JHBox shared drive, which I'll share with you, then I'll upload your video to a YouTube channel for this class. So a poster and you pitching it during this poster session on Saturday, May 12th, and then there'll be a final project report due at the end of exam period, which is Thursday, May 17th. The requirements in the project report are listed here, but you've also seen some examples because you will have looked at the PDFs from the last 3 years. Project video, highly desirable. Probably the best way to show off your project is to shoot a short video. and because people like to watch videos. So, everything clear? Good. All right, so that's the project. Let's get to this week's assignment. We are in week 7, and we're going to do it. So we've worked with sort of what I would call small-scale ROS systems. There's not a lot going on in them. You've had maybe 3, 4, 5, 6 nodes running, and so in simulation, and I chose this one in simulation so that that you can work on it wherever you are during spring break if you're not here. So this will be done in simulation, and we're going to simulate a Turbot 2. The Turbot 2s look like this. We have 5 of them, and Turbot 3s are just being available. Turbot 3 are like an erector set. You can assemble them in different shapes and sizes, and I won't have any Turbot 3s for this spring term, but I'll probably buy some for next year because they're just starting to ship. I want you to read some documentation on the Turbot and read about Turbot simulation in Gazebo. Turbot simulator, kinetic. And then most of you should have taken sensor-based robot motion planning, and so you know about SLAM navigation. It turns out that there's a lot of open source packages for doing simultaneous localization and mapping. And the ROS, the most popular ROS package for SLAM is the Gmapping package. And basically it allows you to drive a robot around in an environment with some sort of a scanner. The scanners that are in vogue these days are laser scanners. And they give you a azimuth and range reading. And basically they use the odometry of the robot to make an occupancy grid. So you drive around an environment, it senses objects, and it defines, it maps out the 2D world as a grid of cells that are either occupied or unoccupied, or I don't know. And so basically if it's shot at scanner between where it is and an object, then it will clear an area and say, well, this area between me and the object is probably unoccupied. And the object is definitely occupied, and everything else is unknown until I've actually seen it or seen through it. And so what you're going to do after you do the tutorials is you're going to run a simulated Turbot 2 in a Gazebo world, and you're going to make a map and save it. And then second part of this is you're going to use an adaptive Monte Carlo localization package called AMCL, which is widely used in the ROS world, and a package called Move Base. And what this does is it's going to load up the map that you generated in the first half of the assignment, and you will be able to specify, and there'll be the Turbot in its environment. You'll be able to specify a goal for it to drive to, and it will simultaneously navigate the robot, and use Move Base to plan a path, a collision-free path to where you want it to go. And so these are some real, some varsity level ROS tools, and I want to walk you through the tutorial. So here's the assignments. Not all the tutorials are updated for kinetic, so there are a few bugs, but I've tried to note on this web page where the bugs are. So I want you to read 2.1 Turtlebot developer habits and 2.2 interacting with your Turtlebot at this site. And if you haven't done it in a while, make sure that you do update your ROS packages. So update. And dist upgrade. And I just did that earlier today, so I didn't download anything, but every few weeks, the ROS folks release another 20 or 30 updated packages. And so if you haven't updated all semester, then you should definitely update now. And you're going to need some additional packages to be installed for the Turbot. So the Turbot installation tutorial is here. Right here, and bring up Turbot installation right there. And you're going to do a Ubuntu package install. And be on the lookout for version conflicts. So they say sudo apt-get install ROS indigo turtlebot. What's wrong with that command? We're not using indigo, right? Right. We're using kinetic. So translate these things into the appropriate version of ROS. And so be on the lookout for version clashes. And so I installed the packages when I was preparing for this. And there's some packages that they specify in this suggested command line that don't even exist for kinetic, or the names have changed. So this command worked for me. So a bunch of kinetic turtlebot packages. Whoop. Go away. So those are all installed. After you install these new packages, make sure that you kill all your shells and create new shells, because when you source your opt-ROS setup.bash, it's going to source a bunch of new packages. And I'd like you to read about the Turtlebot simulator package here, which is available for Kinetic. And don't do a source installation of anything except where I suggested it. And then Gazebo bring up guide for the Turtlebot here. So this is the basic launch file. So we're going to run Turtlebot Gazebo as the package, and Turtlebot world.launch we're going to run. It's going to throw a bunch of errors which you can ignore. You've seen some of the errors, like it complains about the Zacro package not having a -- inline, but it runs just fine. And so this is Gazebo with the Turtlebot in it. And this is the world in question. There's my Turtlebot. This little notch is the back of the Turtlebot, and this is the front. And if we zoom in here, the original Turtlebots that we have connects on them. They're now shipping with these RealSense R200s, which are actually, they're higher resolution than the Kinect, but they've got really crappy range. They're really short range, so I don't really like them a whole lot. And they only work on USB 3, so you need to have a computer that supports full USB 3 in order to use them. So I'm not a huge fan of the R200s. So the Turtlebot is here, and on the web page, they don't actually tell you how to drive it around, so we go to this next tutorial, Explore the Gazebo World. And they give two possible commands. There's this old package called Turtlebot Teleop, Keyboard Teleop. It's kind of a pain to use because you've got to use keys in the middle of the keyboard. And this one down here is easier to use because you can actually use arrow keys. And so I will run that here. And so this only works when this is in the foreground, so I need to make sure that I do that. And so I'm going to take Gazebo, make it small, move it over to the left. And I can interact with this, and I can say I want to go backwards. spacebar to stop. I'm going to rotate to the left. Excuse me. And so I can drive this Turbot around in the Gazebo world. And if I run, sorry. If I run RQT graph, then you can start to see what's going on with the Turbot. So there's a laser scanner going on, there's a mobile base manager, and there's a command velocity. And this is our key out program that's running in a separate window. And it's publishing to turn the motors on and off topic and a command velocity topic, which is a twist. And Gazebo is publishing joint states, and Robot State Publisher is publishing this thing. So there's this simulation in Gazebo, and if we go back to here, we can run this launch file to visualize what the robot is, the data the robot is publishing in RViz, and so let's do that in a new window. So we're going to run, it's Turbot RViz launchers, viewrobot.launch is the name of the file. And so here we have RViz showing the, can people see this, or should I turn the lights down? See okay? Okay, yes? Okay, great. So here's the robot, and notice that the RViz camera is apparently tracking the robot, and if you watch that too much, you're going to get nauseous. The reason it's doing that is that the maker of this RViz initialization file chose the fixed frame to be the frame of the robot. So you can move your camera around, but it'll always move relative to the robot. So if you change the fixed frame to what I would call the world frame in this application, they don't call the base frame world, they call it ODOM. I think it's a dumb name. Now RViz is using the odometry frame, or the world origin, as the base frame. And one could seasick watching this. And there are a number of topics here that aren't perfect because some of them have broken, in the tutorial, they have broken topic names, but we can display the TF transformations for the robot. There's quite a lot of them. So if I turn off the names and I set the marker scale to 0.5, we can begin to see all the frames that are associated with the Turbot. There's one at every sort of sensor location, and there's frames on the wheels and other things. So you can see the ones underneath the robot. There's two wheels, one left and one right, that are rotating, and there's casters fore and aft on the robot. So you can see the wheel frames rotating down there. There they are. And so we've got TF. We have a depth cloud, and the registered depth cloud is even more interesting because once we get the topics right on it, the topics are, the depth cloud, the registered depth cloud has broken topic names, so it needs a depth image, we'll get at that, and it needs a color image, and we'll get at that. And now we've got the depth cloud consists of a series of markers that are at the depth, at the location that the Connect or R200 sensor saw it. And it both paints the markers which are at the position where it found something, and then it texture overlays the color image. So you can see that it's painting out the Jersey barrier here. We're actually looking at the back side of the Jersey barrier because it only sees the front. And we can display an image. The image is not displaying so because the topic is broken, so we'll select a correct topic, and there's the raw image from the RGB depth camera. Oop. Popped out the image by accident. Kill this, close out saving, start again. So global option, ODOM. We looked at TF, robot model, you know about. Grid is the base plane. Image has a broken topic in this demo, so we can pull down the menu. It will give us options of what topics it thinks it can use. Drag that up and make it look a little bit better. We looked at registered depth cloud earlier. We had to fix the depth topic and the image topic, but once we did, then it gave us a rendered point cloud of objects. And this robot doesn't have a laser scanner, but it simulates a laser scanner from the depth cloud. And so if we out of this laser scanner here, you can see this red. There's a Gazebo plugin that simulates a laser scanner based upon the depth cloud. And on the simulated laser scanner, we can choose the size of the markers. So if I make them a little bit bigger, it'll be easier to see. And if I turn off the registered depth cloud, then you can just see the laser scan. Image, laser scan, registered point cloud. We need to fix the topics, and as soon as we do, that's not the one I want. Depth points gives us a point cloud. It's a different way to represent a depth map, and there's a bunch of options on here that you need to read about. But you can see that it's a kind of a nice setup. And if we now look at RQT graph, that's all we have going on. The next thing we want to do is make a map. And make a map and navigate with it. So this is the next thing you're going to do. And I made a note on the course webpage here. The RViz initialization file, when you load this up, is in a system directory. It's in opt.ros, and the launch files are all in opt.ros, and so you can't edit them. So you may find it convenient to clone these two repositories into your Captain workspace so that you can edit the launch files and the RViz initialization files. So to do that, you need to clone this repository and this repository. And I've reminded you, after you clone these repositories, be sure to run cat can make, then ROS pack profile, then kill all of your shells and terminals and open clean terminals, so you'll be using your version of the projects. And I mentioned that the topic names in the initialization file are mostly broken and you need to fix them. So to make a map and navigate with it, instructions are here, and they're reasonably accurate. What you're going to do is you're going to launch three things. You're going to launch Turbot Gazebo and in Turbot World. You can choose a different world if you want. And that's the one we just launched. Sorry. Yeah, so Turbot World.launch. Gazebo comes up, it complains, but either comes up or it doesn't. so there we are. Second thing you're going to want to run to make your map is you're going to run this program, and this is the launch file that launches the G-mapping nodes that'll actually make the map and do SLAM navigation. And so we're going to launch that here. And what it does is it subscribes to the scan topic and the odometry topics. Oh, hang on a second. And you can see it's registering scans, and it's using the odometry, and it's building a map. We can visualize the map in RViz by running this RViz package, the view navigation initialization launch file, and make this smaller. So there's Gazebo over here, and so I'm going to juggle around my two displays so the robot is oriented the same in both displays, more or less. It gets confusing if north is to the right on one display and it's to the left on the other display. All right, more or less. Close. Use the lines on the grid to do the sort of fine alignment. There we go. Okay. And then we need to drive around and make a map. And notice that there's a new thing that's being displayed here, which is a local map and a global map. And we're going to launch a keyboard navigation thing in this window. And I'm going to start by just rotating the robot around. And we can see what's going on. It's imaging this New Jersey barrier. It's imaging this round thing. And now it's imaging the bookcase over here, just the inside of it. And it's declared these areas between it and stuff that it imaged as not occupied, and these things as being definitely occupied because it got a strong return from them. And by displaying both of these things in the same view, you can see what's really going on and what the robot perceives as going on, which are sometimes two different things. And so if I hit my space bar, then things will stop. I'm going to rotate back to the left. Space bar. And the robot's jumping around because it's updating its position estimate. If I drive forward if I'm, here we go. If I drive forward, as it gets views of different sides of things, it updates its map. So now I'm at a different vantage point over here. I'm going to stop and I'm going to rotate. And we'll clear some more area. So we just cleared some more area. And we saw other sides of objects that we hadn't seen before. And so we've got the inside of that bookcase, the square thing, the round thing, and the Jersey barrier. So now I'm going to stop. This is a pretty crappy map. If you drive around more, you'll get a better map. And then to save the map, you'll use this command, ROS run map server minus F. And so I'm going to open a new window. Map server minus F, and I'm going to call it, I'm going to say, map server minus F, LLW map is the name of the map. And so it's going to query the map server. What's going on here? I wanted to show you before we do this. Gazebo, RQT graph. So let's update RQT graph. There's a lot more going on here. But in particular, the SLAM Gmapping node is subscribing to the TFs, and it's subscribing to the scan topic. And so it's using the odometry of the robot, and it's publishing a map topic. And with this command, we're going to pop up a little node that's going to subscribe to the map topic, and it's going to save a map. And what you can see, it said it did. It received a 2400 by 2528 pixel map at 1 centimeter per pixel, and it wrote the occupancy data to map.pgm and the occupancy data to map.yaml. So Emacs LW map.yaml. And so this file just gives the coordinates of the map. It says the image name is map.pgm. The resolution is 1 centimeter per pixel. The origin of the map is at these locations, and the occupancy threshold and the free threshold are these probabilities. Probability of being occupied. And remember, probability can only vary between 0 and 1. Nothing more, nothing less. And so if the SLAM navigation is estimated that the probability of being occupied is greater than 0.65, that marks that pixel as being occupied. If it's less than 0.196, it marks that pixel as being free. And if we browse to temp, and I look at this, I open the PGM file, that's the image file right there. So this is all the field, and these are the definitely occupied, and the white is the definitely unoccupied, and the gray is indeterminate. My recollection is this mapping starts off with a prior estimation of 0.5, so it assumes that it knows exactly nothing about whether a pixel is occupied or not, and then goes from there. So that's the map we just created, and this was the thing that created it. All this is the Turbot stuff. These are the camera and laser scan topics being published. Robot state publishers publishing TFs, and SLAM Gmapping did the work of making the map. So now we can use the map, and we're now here to navigate a map. And this one is a little poorly written, and I've given some hints on the web page. What you want to do is you want to kill everything that you've done before. Start with a clean system. And so we're going to relaunch the Turbot Gazebo simulation. So there it is. And then we're going to ROS launch this in package Turbot navigation. The AMCO is Adaptive Monte Carlo Localization, and I've assigned you some reading to read about that. And you give Adaptive Monte Carlo Localization a map file name. And what they don't tell you very clearly is that the map file name needs to be an absolute reference. So in my case, it would be home, LLW, temp, LLW, map. So that's a full, and I don't need to say whether it's a YAML or a .pgm. It'll know, but I can say that if I want. So, and I've noted on our web page that blah 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 that you need to specify the full path name of the map file, and it'll throw you an error if it doesn't work, and then now we get a map, and now we need to run RViz to visualize it, and you're going to run this visualization version of RViz. You don't need to run the keyboard thing because we've gone beyond keyboards at this point. All right, so we've got RViz here running, and got Gazebo. The default orientations are all different. So this is the Jersey barrier here. So I'm going to rotate RViz visualization so that things are more or less lined up on the two. So there's RViz visualization. And okay. So something screwed up here, so I'm going to need to kill this. AMCL did not come up clean. All right, try this again. That came up, okay. And then we want to do AMCL. That came up clean. We're going to launch RViz visualization. Okay, now we're good in business. So notice that RViz is pretty busy right now. What we can see is it's publishing a local map and a global map. So when we drive this thing, a local map is going to appear around the robot with a fine grid, and we see that there's this whole cloud of little arrows. So what's going on with this? Here's RViz right here, and we can see the Jersey barrier up to the north, and we can see the Jersey barrier here in the global map. And what these are, this is adaptive Monte Carlo localization. So this is a particle filter localizer. And so it's initialized, I think, with 2,000 particles. It's a parameter that you set in the launch file. And you start with a prior, and you tell it where you think the robot is at t is equal to 0, and how well you know it. And in our case, in this launch file, it gives it, the prior is the robot's actual location, but it gives it a very large standard deviation. And so, since it's a particle filter, it doesn't represent this as a mean and standard deviation. It represents it as a pile of particles whose aggregate statistics correspond to the statistics. And so each one of these little particles is a 2D pose, so it's a X and a Y and a heading, and that's why they're represented as little arrows. And right now we haven't been driving around much, and so the system has only got one view of the laser scanner. It's using the laser scanner information in the odometry, and it's trying to fit those data to the map that we made before. And so And so we can do two things. We could pop up the keyboard thing and drive around, but we can also use 2D pose estimate will initialize its pose if we want to force the initialization of the dot cloud. And a 2D nav goal, if I select this thing, will allow me to put down a two-dimensional navigation goal. So I can say, robot, go from here to this location with that orientation. And a local map pops up. And this is the local map that's just popped up. And it did sort of an okay job of driving to that pose. It did a bunch of twirly-whirlies, and the adaptive Monte Carlo localization, notice that also in doing so, it turned around, and you can't see it very well here. If I turn off the local map, notice that the dot cloud really resolved itself, and they're all pretty much pointed in the right direction, and they're grouped really closely. So by making the observations as it spun around, that cloud, the confidence of its estimate got much higher. And so I can choose, I'm going to pop up the local map to global map and the local map. And if I give a different 2D nav goal, I say drive over to here. That's a pretty easy nav goal. You can just drive straight ahead. What if I say I want a 2D nav goal, I want to drive over to the bookcase, see how well it does. Yeah, it's doing the twirly-whirlies. So this is what's called a clearing behavior, where if it's uncertain about its location, it'll just do some circles until it figures things out, and it's not particularly helpful. So the designers of this tutorial, I don't think they chose very good parameters for AMCL, and so on the web page I've suggested that you might want to modify the parameters, and you can do this either by editing the launch file, or one of the future topics that I'm going to cover is dynamic reconfigure. And so to run dynamic reconfigure, this is the command. We're going to tune some parameters in this to make it behave better. So our RQT reconfigure pops up user interface that will allow us to tune some parameters for AMCL. And so these are I've asked you to tune the move base parameters to disable the recovery behavior and the clearing rotations, which were the twirl-whirlies, and then go into the navigation velocity smoother. No. Yeah, in the navigation velocity smoother, make the advanced velocity speed 1 rather than 5. Slow down the robot a little bit. And those parameters are updating on the simulation automatically. We could have done that by editing the launch file, relaunching. And when we do that, navigation improves. So I can give a 2D goal. Let's try to drive over here. So you can see the point cloud. See, it's no longer doing the clearing moves of going around and around. And it's doing autonomous navigation based upon its sensors. So this is really a pretty powerful demonstration. There's a lot going on, a lot of new things, and when you look at the launch file, you see there's a whole list of about 50 parameters that go into this thing, and it takes some experimentation to get it to work properly. That's one of the open dark secrets of some of these navigation methods is that they're not very robust and you need to tune them a lot. And if we go back to RQT graph, which here, and I refresh, whoa, what's going on here? A lot. So here's Gazebo, and it's publishing a bunch of sensor topics, and then this is these are the nodes that control the robot, and they would run whether the robot was simulated or real. And Gazebo is publishing joint states, robot state publisher, This is a node that takes a depth map and it publishes a fake laser scan. And this is the move base node that is publishing all these things. There's a whole bunch of things: local map, cost map, and the AMCL algorithm that's doing the navigation is here, so they're separate. So AMCL is publishing the particle cloud and particle descriptions and TFs on where it thinks the robot is. The map server is publishing the map that we created previously. The map's not being, it's static at this point. And MoveBase is using the map and all the knowledge of AMCL. So this is sort of the first really sophisticated example of using some very sophisticated packages such as AMCL and MoveBase along with a simulated robot to put it all together and to be able to navigate the robot autonomously. So go over there. Get the idea? Okay, that's what I wanted to cover this week. Thursday's class will mostly be a clinic. I ran out of time, so I won't do the robot of the week today. I'll do it on Thursday. Has anybody seen the 1968 Stanley Kubrick film, 2001? Yeah. I remember seeing it when it was first released. It was pretty young. Okay, that might be one of our robots this week, the HAL 9000 series. Give robots a bad name, and artificial intelligence in particular. Any questions? All right, I want you this is a fun tutorial. Take your time at it, and I'd like you to also introspect not just into RQT graph, but look into ROS topics for this, and you'll see that there's a very rich set of ROS topics, and you can introspect onto them. ROS topic list. There's a whole crap load of topics out there that are being published, and this is the first example of a really full-up ROS-based system that does a lot of sophisticated things. See you Thursday. Thanks, everybody. If anybody wants to demo this week's assignment, then Soam kindly came over, and Soam and I can witness your simulated robot driving around in the world.